In the vast darkness between galaxies, where gravity sculpts the cosmos into webs and clusters, the James Webb Space Telescope spotted something that should not be there. A structure so immense, so sprawling across the cosmic landscape, it defies the boundaries set by our best physical models. It is a cosmic puzzle, and it challenges everything we thought we knew about how the universe's largest structures form and evolve. The discovery came as part of Webb's deep field surveys, where its gold-coated mirrors peered back over 13 billion years in time. What astronomers expected was a tapestry of galaxies arranged in patterns consistent with the cosmic web. This web is woven by gravity, pulling dark matter into strands and nodes, with galaxies sprinkled like beads. But this new structure looks more like a sprawling supercluster, a vast congregation of galaxies, gas, and dark matter, stretching across a length that should be impossible for its age. How immense is this? The structure spans roughly 1,500 million light-years across. To put that in perspective, our Milky Way galaxy is about 100,000 light-years wide. This cosmic giant is 15,000 times broader. It could easily swallow thousands of galaxies like our own and still have room to spare. According to the standard model of cosmology, based on cold dark matter and Einstein's general relativity, structures above about 1,000 million light-years across should not have had time to form since the Big Bang. That limit is known as the cosmic homogeneity scale. Beyond that scale, the universe is expected to be smooth and uniform. The discovery of a single structure stretching well beyond that scale throws a wrench into this neat picture. It means the assumption of homogeneity, the foundation of modern cosmology, might not hold true at these gigantic scales. The idea behind this cosmic homogeneity comes from the early universe's uniformity, measured by the cosmic microwave background. Tiny density fluctuations were small enough that the cosmos looked smooth when averaged over large enough volumes. Over billions of years, gravity amplified some of those slight peaks into massive structures, but never beyond a certain size. The boundary is critical because it underpins the mathematical models used to explain dark energy and cosmic acceleration. So, what exactly did the James Webb Space Telescope see? The structure was detected through a combination of bright distant galaxies aligned in a filamentary manner and spectroscopic data confirming their similar redshift. These galaxies form a connected chain, or filament, with smaller galaxy groups clinging to it. The arrangement is not a chance alignment, but a real physical structure. The redshift of this structure is about 6, meaning its light has traveled over 12 billion years to reach us. This places it in a cosmic era before the universe was 1 billion years old, still in its infancy. Our current simulations do not predict such massive structures existing that early because matter simply has not had enough time to clump on scales that large. The size and age of this cosmic giant raise urgent questions. How could gravity have pulled together so much mass so quickly across such an immense scale? Are our models missing an ingredient? Is there some unknown physics or new form of dark matter at play? Or could the observations be revealing an error in our interpretation of the data? The team responsible for this discovery includes astronomers using Webb's near-infrared camera and mid-infrared instrument, which can detect extremely faint objects across cosmic epochs. They combine this with data from powerful spectrographs to measure galaxy distances precisely. The combined imaging and spectral analysis was essential for mapping the three-dimensional shape of the structure. This challenge to cosmic homogeneity is not entirely new. The discovery echoes previous reports of enormous structures like the Hercules Corona Borealis Great Wall and the Sloan Great Wall. Those also stretched beyond expected limits, though some remain controversial due to data quality and interpretation issues. But the Webb detection is different. It's one of the earliest and clearest examples found at such a high redshift. Webb's unprecedented sensitivity and resolution provide the clearest window into these early cosmic times. Its infrared instruments penetrate the cosmic haze of dust and gas that blocked earlier telescopes. This allows it to gather light from faint galaxies forming when the universe was less than 10% its current age. The extraordinary scale of this newly discovered structure forces us to revisit the assumptions in the lambda cold dark matter model. That model is currently the cosmological standard, incorporating dark energy made of a cosmological constant termed lambda and dark matter as cold, slow-moving particles. It reproduces many details of the universe's expansion and structure formation, but predicts certain scale limits for object growth. If confirmed, the existence of a 1,500 million light-year structure at redshift 6 would break those scale limits. It may mean dark matter evolved differently than thought, or dark energy may have varied over time rather than being constant. There is also the possibility that the laws of gravity themselves need modification at cosmic scales. A more subtle option is that the structure is not a gravitationally bound supercluster in the usual sense, but rather a chance alignment of galaxies along our line of sight, masquerading as a coherent structure. The teams carefully tested this with spectroscopic redshifts and statistical models, but the question remains open for further observations. Either way, this discovery reopens a fundamental question that cosmology has wrestled with since before Webb. How uniform is the universe on its largest scales? It forces astronomers to examine the cosmological principle, the assumption that the universe, on average, looks the same in every direction and position. This principle allows simplified equations and predictions. But if massive outliers exist, those basics fall apart. Some theorists argue that the universe might be fractal in structure, even on the largest scales, that there is no true scale of homogeneity. In a fractal universe, galaxies and clusters could organize at every scale, no matter how large. This would drastically change how we understand cosmic initial conditions and evolution. That perspective, still fringe, gains new attention because of Webb's observations. They show the universe may be more complex and structured than the neat grids and webs drawn by simulation codes. This challenges not just physics, but the nature of cosmic randomness and causality. Behind the scenes, Webb's data processing involves huge computer simulations run on supercomputers. These simulate billions of particles of dark matter and gas to model cosmic evolution. The simulated volumes rarely produce structures larger than about 1,000 million light-years at redshift 6, reinforcing how anomalous this new Webb structure is. To resolve the growing tension, astronomers plan to expand the search for similar objects using Webb's other programs and newer observatories like the Vera Rubin Observatory. If more enormous early structures appear, it will force a major rethink of cosmology. Competing explanations also include more exotic physics like early dark energy bursts, modified gravity frameworks such as theories extending Einstein's relativity, or new particle physics influencing structure growth. Some theorists suggest interactions between dark matter and dark energy could accelerate clustering beyond standard models. Whatever the answer, Webb's capacity to see these extremes pushes science beyond its comfort zone. The telescope launched with goals to glimpse first stars and galaxies, but has already shattered expectations by revealing something larger, older, and more complex than anticipated. This is the part that once keeps cosmologists awake at night. If the cosmic homogeneity scale is not a hard boundary, but just a guideline, the very foundation of universal evolution models cracks. Predictions about the fate of the universe, such as eternal acceleration or eventual collapse, hinge on those basic assumptions. So, what are the implications beyond astrophysics? In some sense, this giant structure is a mirror on human knowledge itself. It reflects the limits of our assumptions and models, and the way our picture of the cosmos is always provisional. Telescopes like Webb don't just collect light, they illuminate our blind spots. Astronomers will continue analyzing Webb's deep field data to extract every clue. One key step is cross-checking with observations from other wavelengths, like X-rays or radio waves, to map gas and dark matter distribution around the structure. Another is measuring galaxy velocities to assess gravitational binding. The tension also raises interesting philosophical reflections. It challenges the Copernican principle that Earth and its surroundings are not special locations. If huge structures falsify cosmic uniformity, it may imply we inhabit a more unique place than thought. That does not mean Earth-centered cosmology, but it complicates the idea of cosmic mediocrity. More comprehensively, this discovery dovetails with a string of growing tensions in cosmology today. The Hubble constant discrepancy, the nature of dark energy, the properties of dark matter, all of these add stress. The Webb structure adds one more thread, unraveling the tidy cosmic tapestry. What Webb has uncovered is a cosmic outsider, a ghostly giant lurking in the early universe, calling into question the homogeneity scale and the physics beneath it. It invites scientists to expand their theories or imagine new forces and particles. Ultimately, the James Webb Space Telescope has done more than find a record-breaking structure. It has cracked open a door to new physics, pushing the boundary of the known universe itself. This structure is the universe whispering a secret we weren't ready to hear. Thanks for watching, and I will see you in the next one.